Hello, welcome to lecture 17 for Math 155. Today we're going to be talking about integrating volumes. Note that there was no lecture 16 for Math 155 because that was reviewing material from Math 154 about integration. So we're going to be taking those ideas forward today and thinking about functions in multiple dimensions, and that will allow us to calculate volumes. Okay, so suppose we want to find the rate at which blood is flowing through a vessel. And this particular function here, which we don't need to know the details of where this all comes from, but essentially tells us the relationship between the pressure of the blood, the viscosity, which is given by this Greek letter eta, the radius of the blood vessel, and how far away from the center line you are measuring. So this basically says that when you are, when little r is equal to big R, when you're right at the boundary, there is no blood flow, and when you're at the middle, the flow is maximum. Okay, so there's this relationship here. How can we work out what the total rate of blood flow is through this vessel? Well, what we can do is we can think about adding up lots of little rings where we calculate the approximate area of any ring. So suppose this is looking head on, and we just want to say, okay, we want to calculate the area of this ring. So this one that's highlighted here. So we can assume that our delta r, the change in radius, is quite small. And because of that, we can approximate the area of the ring as going to be fairly close to its circumference. So this is just going to be 2 pi Ri, so this is the ith ring, times by delta r, which is just going to be 2 pi Ri times by Ri minus 1. So in other words, the radius of the ith ring minus the radius of the next one in. So this radius here is going to be Ri minus 1. Okay, so we can approximate the area of this ring, and then we know that our rate at which blood is going to flow through, in other words, the volume of blood per unit time, is going to be area times velocity. So we're going to have 2 pi Ri times by delta r times by our function v of Ri. So this is the v from this previous slide here. So that'll give you the volume of blood flowing through a particular ring. We want to know what's the volume of blood flowing through the whole blood vessel. So this means that we need to take the total flux, the total amount of blood flowing through this blood vessel. We're going to sum over all possible rings. So if we divide this up into n different rings, we're going to sum over these n different rings, and they're going to be 2 pi Ri times by v Ri times by delta r. So if we're going to assume that there's a constant delta here. So what does this mean then? Well, if we take the limit as n tends towards infinity, so we're going to make this delta r get smaller and smaller and smaller, then this sum, so just rewriting out from the previous slide, this sum 2 pi Ri times by v Ri delta r is going to tend towards the integral from 0 to big R. So big R, remember, is the radius of the blood vessel, of 2 pi little r vr dr. So this is going to be limit as n tends towards infinity. So we're taking smaller and smaller rings, we're taking more of them. This delta r here becomes this dr in the integral. So we can take out this 2 pi to the front and then substitute in our function for vr. So remember, this is just p over 4 pi eta L times by r squared, big R squared minus little r squared dr. So all that is that's just this v r from the beginning. Okay, so we have this integral here. Well, we can work out that integral. It's a definite integral. So if we take out this factor of p over 4 pi eta L to the front, we can rewrite, actually we can just jump straight ahead and do the integral here. We're going to have little r squared times by big R squared over 2 minus r to the 4 over 4. That's because, recall, we've got this little r here, so that's going to multiply each of these terms in the bracket here. We're going to evaluate this at r is equal to 0 and r is equal to big R. So these pi's cancel here, the 2 cancels there as well. We end up with p over 2 pi L times by big R to the 4 over 2 minus big R to the 4 over 4. And then we're going to have minus 0, minus 0, minus 0 plus 0, in fact. This ultimately ends up giving us p r to the 4 over 8 eta L. So in a blood vessel of length L, where the blood has viscosity eta, and we have blood pressure P, and the radius of our blood vessel is capital R, this gives us the rate of flow of blood per unit time. Okay, so what we did there is we split up our problem into a much smaller problem, summed up all those smaller problems, and then gave us an integral when we took our limit. And that's kind of a theme that we'll see going on through here. Now, in one dimension, we found the area under a curve by summing up lots of rectangles. Now we're going to be summing up lots of bits of volume underneath our surface. Okay, so it's a similar process. Suppose we want to work out the volume under this surface here. Well, we need to work out with these little delta x's and delta y's. So it's going to be our delta x here. This is our delta y. And we're going to have a height for each of these blocks. So this block here, for example, is going to have height equal to f of, say, x star, y star. Okay, so we work out the height of all these different blocks, and then the volume is just going to be equal to the area of the base times the height. So we know the area of the base, that's going to be delta x times by delta y. And the height is going to be our function, f of xi star, y j star. So this is exactly the same process as we were doing in one dimensions, but we've just increased the dimensionality now. So now we're doing volumes rather than just areas. So we can do exactly the same process we did with our Riemann sums in one dimension. If we have more and more different bits to add up, then our approximation is going to be more accurate. So in this case, over on the left-hand side, we've only got 4 different volumes. It's not going to be very accurate. As we move to the right here, and as we eventually tend towards infinity, as we have more and more of these, our approximation is going to become more accurate, and it will tend to it in the limit. So if we want to calculate the volume of a function using this method by heights, we can limit ourselves first of all to a rectangle of where we're integrating over. So there are some boundaries A, B, C, D. You can recognize being the X and Y bounds here. We can work out what our delta X and delta Y are based on those boundaries and dividing them up into n little bits. And then we can approximate the volume of our surface by summing over in both the X and the Y directions this product here, which, if you recall from the previous slide, was just our height of our little volume times by the area of the base. And then if we take the limit of this as n tends towards infinity, these turns into integrals, and we have this iterated integral here. So it's very similar to what we did in one dimension, but now we've just got an extra sum, which turns into an extra integral. Okay, so let's approximate a volume underneath a surface using the midpoint rule. Okay, so we can use essentially this formula up here, but without the limit, and substitute in our A and B values. So this is going to be our A, this our B, this our C, and this our D. So we know from our definitions, which I'll leave just up there, that A is equal to 1, B is equal to 3. So our delta X is going to be B minus A, which is 3 minus 1 over 2, which is just equal to 1. And then our C is equal to 2 and D is equal to 3. So this means that our delta Y is going to be equal to 3 minus 2 over 2, which is a half. Okay, so what we want to do now is we want to work out what are our midpoints. So if we imagine for a second what we've got going on here, we've got a rectangle, we've got our X values, 1, 2, 3. And then we've got our Y values, 2, 3. And if I call this one 2.5 in the middle, what we're doing here is we're splitting up our, just going to put those on there, the X and the Y directions. We're splitting up this volume into these 4 different regions here, and we're going to calculate the midpoints here, 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 and here, and approximate the volume underneath this surface using those midpoint values there. So we can call this point here x1 star, this one here x2 star, and likewise in the y direction we can have a y1 star and a y2 star. So what's left now is to work out what our x1 star is and so on. So x1 star here, that's going to be midway between 1 and 2, so that's 3 over 2. Likewise, x2 star is going to be equal to 5 over 2. And then in the y direction, we're going to have 9 over 4 and 13 over 4. So these are just these midpoints here. So halfway between 2 and 2.5 is 9 over 4. Halfway between 2.5 and 3 is 13 over 4. Okay, so we want to work out our sums. So our sum is going to be equal to the sum, because we've got 2 of each of these, sum from I is equal to 1 and there should be a j is equal to 1, both of them up to 2. We're going to have our function, so 2xi plus xi yi times by our delta x times by delta y. So that's just using this up here, this formula for our volume here, but without the limits. So we've only got, we're breaking this up into 2 pieces because we've got n is equal to 2. So, sorry, 2 pieces in each dimension. So we get 4. So this ends up giving us S2 is equal to, well, the first one is going to be 2 times by 3 over 2 plus 3 over 2 times by 9 over 4. So we're taking our x1 star and we're multiplying it. Here we've got 2 times by x1 star plus x1 star times by y1 star. And then we add this to all the others. So we end up with 2 times by 3 over 2 plus 3 over 2 times by 13 over 4 plus 2 times by 5 over 2 plus 5 over 2 times 9 over 4 plus 2 times by 5 over 2 plus 5 over 2 times by 13 over 4. So that gives us our function bit, and then we need to multiply this by our base and our height. Remember our delta x, which is our part of our base, is there, and our delta y, the other part, is a half. So you have this times by 1 times by a half. If you work this all out, I believe it comes out to be 19. Okay, the value doesn't really matter here. What matters is the process that we've taken to do this, to approximate the area under this function with just a value of n is equal to 2. So we're splitting our x and y dimensions just into 2 blocks each, giving us a total of 4 blocks. What we're doing is we're working out the area, the base area of each of these different rectangles. and then calculating the height, multiplying those two things together, and then adding all of those up for all those different blocks. So there's 4 different blocks here. When we do that, we end up getting 19. So this blue one here is corresponding to this one here. Okay, so that's one way in which we can do things. Another way is to think about cross sections. So rather than thinking about volume under a surface, we can think about integrating volumes by looking at a cross section. So you can think of taking slices. So imagine this is, say, like a loaf of bread. You can think of these as bread slices. We're going to take very, very thin bread slices through this. Each of those will give you a cross section. And what we're going to do is we're going to sum up all those different bread slices as they get very, 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 very thin. And then that will turn our sum into an integral. Okay, so if we picture an infinitesimally thin slice of bread, just as we have here, so we're taking a slice through our volume. Suppose this is an organ and we want to calculate the volume of that organ. We're going to take a slice through this, and then this will give us an area. So we can work out this area, this capital A of X, say by working out the area under a curve. For example, it might look something like this. We work out our area. It might be an area between two curves. Suppose it's something like this. We work out our area, our A of X. We're going to do that for every value of X. X is going in this direction here. And then we're going to add all of those up. And as this is infinitesimally thin, this turns into an integral. So if we add up all of our areas, that will give us a volume. In other words, an integral of area is volume. So this down at the bottom here, this definition is essentially just summarizing that. If we have an area for a given cross section, so xi is, if you imagine we're moving along the length of this object, and where you are in terms of the length is given by the x coordinate, the area corresponding to that cross section at xi, or xi star, we have our width of that cross section, and that as we take more and more cross sections, as n tends towards infinity, that delta x is going to tend towards 0, and this whole thing here turns from a Riemann sum into an integral. So we can use this method to approximate volumes. For example, the volume of liver. And essentially what a CAT scan does is it produces lots of cross-sectional images of a human organ, and then you add those all up and you calculate the volume. And then you can, for example, see how the volume might change over time due to disease. So suppose, for example, we have a CAT scan of a human liver, which has cross-sections spaced 2 centimeters apart, and the liver is 20 centimeters long, and then we have these different areas measured as we move across the length of this organ. And then we're asked to use the midpoint rule with n is equal to 5 to estimate the volume. So how do we calculate that? Our volume is going to be approximately equal to, well, n is equal to 5 and the length of the liver is 20, so we have 20 divided by 5, 4 centimeters times by the sum of our areas. Okay, so we can picture this as being something like this. If we have, say, this are 20 centimeters, let's just split this up, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. These are the measurements that are taken at 2 centimeter intervals along the length of the organ. And then we can plot on what our areas are going to be. So our first area is 0. The second one is 39. So it's going to look something like that maybe. Then 63, 128, 117, 106, 94. This isn't going to be particularly accurate, but we just want to get an idea of roughly what this looks like. 18 and 0. Okay, so that's probably quite inaccurate, but that's roughly what the areas look like. So these are going areas. This is call this our x, our length. And then because we use the midpoint rule at 4 centimeter widths, so n is equal to 5, we've got a 20 centimeter long liver, so each block we're going to calculate is 4 centimeters long. We're going to use the midpoint rule, so we're going to use the midpoint to estimate this, so we're just going to pick out the midpoint as the height of each of these. Okay, so we draw these on, we'll get something that looks like this. And so to calculate this volume, so our volume is going to be approximately equal to, well, these are all 4 centimeters wide. So we're going to have 4 centimeters times by, well, let's sum up all of these different areas here. So we're going to use this value, this value, this value, this one, and this one. So it's going to be every other one. So we're going to have 39 plus 128 plus 106 plus 79 plus 18. And these are all areas, remember, so these are going to be centimeters squared. That's going to give us 1480 centimeters cubed. So this gives us the volume in centimeters cubed of our liver, approximated using the midpoint rule. Of course, if we took more measurements, then we would be able to approximate the volume of this liver better. Okay, the final thing we're going to talk about today is volumes of revolution. And this is because many physical objects have a rotational symmetry. So for example, if you think about a ring donut, that's essentially just taking a circle and then rotating it 360 degrees. There are lots of objects that have that kind of rotational symmetry. So we can also use this fact to help us calculate volumes by thinking about that rotation. So if we have, for example, a situation like this, if we look sideways on to this object on the right-hand side, we'll have something that looks like this, and we can think about the outer radius, this r out, compared to the inner radius as we move along in the x direction here. Okay, so we can think about how the area of a disk, so suppose this, we're interested in the area of this disk here, this is r out here, remember, so this distance to this outer point here is r out, and the inner point is r in, and the width of this is going to be delta x. And this disk, if we just focus on the cross section, it has area pi r out squared minus r in squared. So that's just working out the area of that disk if we just look at it head on. And because it is delta x wide, it's going to have volume equal to delta x times by pi r out squared minus r in squared. So now that we know the volume of this disk, we can work out the volume of the entire object by integrating over its length. When we do this, the sum that we had previously as well would turn into an integral. And we have this pi out the front because we have this rotational symmetry, and we just need to then think about how the radius of the outer part is changing relative to the inner part. This is sometimes referred to as the washer method because this here looks a bit like a washer. You can also see it related to something called the disk method, which is when essentially we are rotating an object that is sat on the x-axis around the x-axis. So that means that just our r in is equal to 0. Okay, that's it for integrating volumes today. I'll see you in the problem class.